So I will be talking about the NIRSpec IFU. And as Tracy already introduced me, I'm from the ESA NIRSpec team in Baltimore, and I'm working on the NIRSpec IFU. And since I am the first talk of IFUs this day, I can also introduce you to IFUs, but I think I don't have to, but just to remind you what kind of IFUs or what an IFU actually is. This is this slide what everybody likes to show every time we talk about IFUs. There are several ways of making an IFU. You can just put basically the lenslets right in the focal plane and disperse them where they are. So this is the first one. Do we have a pointer? Oh, it doesn't matter. And the next one is using fibers. That's done by telescopes at the VLT, for example. What we do? OK. Ah, a pointer. Really good.
Put it on.
OK. And I switch it on. There we go. Yeah. Yay. OK. Good. So that's the second part where you just use light fibers and then put these ones into a slit, disperse them, and you get the data cube. Or the last one, and that's the one which is used nowadays quite often, the slicer version, and this is also used by the NIRSpec IFU and the MIRI IFU, where you use mirrors to slice the image, disperse the image, and then get your data cube. And the final product is a 3D cube where you have x and y and lambda in the z direction. So this is an overview of the NIRSpec IFU, just for you to, you have heard this before now in the previous talks. Our IFU is, as I said, a slicer module. We have 30 slices. Each of these slices is 0.1 arcsecond. So if you want to have a quadratic pixel, you have an 0.1 times 0.1 spaxel. And this all together gives you a 3 times 3 arcsecond field of view. Then the configurations is the same as for the other modes in NIRSpec. You can have a very low resolution, but therefore the entire wavelength range with the prism. And then you can have the two different modes with the medium resolution and the high resolution gratings. So this is just as a reminder. So it works the same as for the MOS and the fixed slits. And this is our throughput. It goes pretty high up, above 3 microns. And below 3 microns, we are always above 50%. This is just informative. We decided to put a slide with the sensitivities on each of our modes. And same as Thorsten said, I put a disclaimer here that whenever you want to really have the values, please go to the exposure time calculator. This is all still very preliminary, but it's just like an overview for you. That's how our sensitivities look like right now, but they might still change. And we will see that only final once we are in flight. So where is the IFU located? I'm not going to explain the entire instrument again. You've seen that with Thorsten's talk. This is the NIRSpec instrument. And I just want that to point out where the IFU is actually sitting. And it sits right here at the MSA. And this is how it looks like. It looks a little bit like a piano, my opinion. But this is the entire IFU. Everything of the IFU is in this little thing, which is quite remarkable. From the light path, this is how it goes. We start here at the pickup mirror, and then we go through some relays, where we go to the most important part, which is the slicer. So this is this mirror, which is actually slicing our image by just reflecting it in all different ways, putting it into the pupil mirror, and then out again, where it will be dispersed. And then at the end, we can build our 3D cube. And how does that look on the detector? So here's an outline of the NIRSpec detector. You see our 2 detectors here with this white big lines, and our 4 microshutter quadrants. And this little thing right here is actually the IFU opening. You won't see it like this on the detector. This is just for you to understand where it's actually located within all the shutters. And this is how it looks like after the light came out of the IFU. So those are all the 30 slices that we get from the IFU. And you see it's actually on the same area as the quadrants, and that is causing some issues, but I'm coming to this in a second. So this is how it looks dispersed. So this is where the spectra go. Those are the fixed slits, and those are all our IFUs. So in simulation, and now in real world, again, fixed slits and our IFUs. And you might notice that there are some other things that are a little bit annoying in that image. Those things here. And those are our little micro shutters. Those are the failed open micro shutters of the MSA. And this is actually a part of a big problem with the IFU, which is called MSA leakage. And it's not just the failed open shutters, it's also like what you cannot see in that image very well, but you saw it in Torsten's talk, is the limited contrast of the MSA, so that light is actually leaking through even closed doors. And when you have a very long exposure time, you actually see it in the background of your IFU. So you need to get rid of this. And the way to do this is actually to do another exposure with the IFU closed. Because you can do this, we have this little latch here at the magnetic arm. And if you move the magnetic arm in front of the IFU, you will close it, no light can go through. And then you get a pure leakage exposure of your science exposure, basically. And then you only have to subtract one image from the other, and you get a nice clean IFU image. Of course, this is causing overheads, and there's still a lot of development trying to optimize this in the best way. Since we can actually subtract that on the count rate level, we might be able to really scale it up, and we don't have to observe in the same time as our science exposures. And this is just to show you how it looks extracted with our pipeline right now. We start with a 2D trace where we basically cut out all the 30 slices in a trace, and we assign them both wavelength values and Y values. This is then used to make a 2D rectified, where it's all going to be nicely spread on a 2D grid. And then you can use that to collapse the 1D spectra, something like this, and put it in a cube. So this is actually the product you get on your USB stick. It's just a final cube with spectra in each of these spaxel, but Giovanna will tell you more about that. So now let's look at it in the APT. This is the APT, how it looks right now. And this is not final yet, because especially for the IFU, we will still add a lot of things here. So you can choose your target acquisitioning here. IFU is fine with point and shoot most of the times, except you want to put your target in one of the slices. But most of the time, you can just start observing. Our accuracy is high enough for that. And here you will choose your dither patterns. I'm going to say something about this in a minute. These are still the old dither patterns. And here you basically choose your configuration, your filter, your grating, your number of groups in integrations. And also you can put an autocall here, which is right now, I think, just the wavelength calibration. And right here, we will add two new columns, which have something to do with the leakage exposure. And I photoshopped those in here. So we will get a column called leak call, and we will get a column called dither. So leak call, you can choose yes or no. And if you say no, it's a science exposure. That's fine. You can duplicate that and then say yes. So this is now your leak call exposure, so the exposure for the MSA leakage. And then the dither column will tell you, so when you do science, it will not be editable. You cannot do anything with it. It will just display what kind of dither you will do. So you can just leave that alone. If you do a leakage exposure, you can choose between yes and no in this column. And when you say yes, you will do a leakage exposure at all of the dither patterns of your science exposures. And if you say no, you will just do it at the first dither position of your science. Because sometimes if you do really small dithers, you might not need to do a leakage exposure on all of the dither positions, and you can just use one of them and then subtract it. I mean, that depends on your science case, and we just wanted to leave the user this kind of flexibility to do that, because it is a very big overhead. And as you see, you can also adjust your exposure times for the leakage exposure, so you don't have to do it the exact same length as the science exposure. So to save some time, and you might be able to scale it. But this is all, we need to find out how that works and experiment with that a little bit. So, but we want to give the user the flexibility for this. And then another thing, what I really like is this mosaic properties, because from observing experiences, as I think everybody has had that before, when you try to make mosaics, it was really annoying to calculate the shifts and then put them in the right way as coordinates in the planning tool and so on. But with this, you just can tell it, oh, I want a 3x3 mosaic, and I want a 10% overlap, and it's doing everything for you. And I think this is really nice. This is how it looks like. So this is now an exposure with 3x3 mosaic and some dither patterns on it. And, well, I'm going to get tangled here. So, and since I talked about the dither patterns, last but not least, I'm going to tell you a little bit about the dither patterns here. So this is still very preliminary. We're still discussing this. It's discussed in the moment, but this is what we have so far. This is the dither patterns we want to offer for the IFU. We will have a 2-point knot, a 2-point dither, and a 2-point knot, a 4-point knot, and a 4-point dither. And the only difference between the knot and the dither here is that the pipeline will actually do background subtractions with the knot, but not with the dither. So physically, the 4-point knot and the 4-point dither are the exact same thing, what the telescope does. But when later the data will be processed, if you have extended sources, you don't really want to make a background subtraction, you select dither, and then you won't do that. And they will have about a 2 arcsecond extent. And as you can see, we have here 0.25 pixels, so we actually have sub-pixel dithering here. And then we will have a 60 cycle, where we have 60 points, where you can actually choose whatever point you want. And you have actually the first 9 points of the 60 cycle is a 9-point dither, or a 2-point dither, or a 4-point dither, or a 5-point dither. So again, you can do your dither patterns in this extent. And it will also be offered in 3 different extents. So you can have really, really small dithers or really big dithers. So you will be able to choose between small, medium, and large dithers for the 60 cycle. So this is very similar to what MIRI is also doing. And the rest of the points of the 60 cycle are actually Gaussian, chosen from a Gaussian distribution. Good. I think I was pretty fast here, but I'm just going to summarize that in one slide so that you have an overview of the NIRSpec IFU. Again, it is an image slicer. It has a field of view of 3.3 times 3 arcseconds and a spaxel size of 0.1 times 0.1. Physically located, it is at the MSA, and on the detector it coincides with the MSA traces, which causes some issues, for example, the leakage, the MSA leakage. To get rid of the MSA leakage, we have to do at least one exposure with the IFU closed and subtract that. But as I said before, you can probably trick around a little bit, and you don't have to do it after every exposure. For the MSA leakage in the APT, you will get, so it will be done after the science dithers were done, and then you can choose whether you want to do it at the first dither position or at all dither positions by just specifying this in the dither column. And you can also adjust the exposure time. Well, and then you can adjust dithers and mosaics in the APT as well. And the dither patterns will be a 2-point, a 4-point knot, and a 4-point dither to a 2 arcsecond extent, and then a 60 cycle with 3 different extents. So you can pick and choose what kind of dithers you want for your specific science case. That's it. Thank you.